all, I'd like to thank the organizers for attending this book. It's a real pleasure for me and a great honor to be in this place, sharing some ideas with you, especially in celebration of a great mathematician's birthday. So let me start by noticing that the short length between of the bridge that joins pure and applied science is one of the favorite topics for discussions, especially when it comes to presenting science to public in general, which I guess is not the case here. So following this trend, and because of the place that we are in, I'd like to focus this talk into presenting two concrete instances of problems of this connection between applied and pure science that involves actually work that Sam has done over the years. Actually, it will be dealing with the first things that he was working on, and then more recent stuff. So yesterday, Don Davis already gave us some updates and general view of the generalized vector field problem, namely geometric dimension, stable geometric dimension of vector bundles over real projective spaces. And a particular problem of this problem is the immersion problem for real projective spaces. And indeed, this is one of the first problems in which Sam did a lot of work, fundamental work, and now it's connected to one of the most fundamental situations in robotics. Namely, in short, the motion planning problem arises when one has to instruct a robot how to move, how to achieve concrete tasks. Like a car, the robot has been designed and constructed with very specific and sophisticated capabilities of movement, but the robot, of course, lacks of the human intelligence to organize a series of actions to perform concrete tasks. So the goal is for us to teach the robot how to do these actions with two conditions. The first one is that the task should be will be assigned in real time, and the other one is that it should be executed without human supervision. So, depending on the point of view that on the tools, mainly on tools that you want to use, there are several ways of approaching this motion planning problem in robotics. And one of these approaches was proposed by Michael Farber at the University of Warwick in England by the beginning of this century. And Farber's model is quickly captured the attention of many topologists because it fits very naturally with the philosophy in algebraic topology. So let me describe very briefly what this model has to do with. So suppose you have a robot and you look at the space of states of this robot, namely all possible positions that the robot can reach. For instance, this space would be the surface of a donut, a torus, a two-dimensional torus, if your robot consists of a mechanical arm of three bars, where the first one and the second one is joined by a planar join, and the same thing for the second one. So essentially, you have 2 degrees of freedom for moving, and this describes a torus. So in this sense, you can think of the space of the Cartesian product of X with itself as the space of tasks. Namely, a task will be represented by a pair of points, A, B, where A is the initial position of the robot and B is the final position of the robot. So somehow you're concentrating on the path motion planning problem. Then a solution for such a task would just be a path, continuous path, starting in A, ending in B, and a motion planner would be a function assigning to each task a solution for it. In other words, it is just a section of the evaluation map, EX, that sends a path into the endpoints. Now, there is well, usually in practice, there are lots of parameters that one has to take into account, and many of them are actually out of our hands controlling. So let me refer this as noise. And I want to produce, well, the objective, one of the goals is, in practice, is to produce motion planners that best control the problems provoked by noise. Now, for instance, this noise can affect the way that we let the robot know what are the tasks to solve. For instance, if in a noisy environment, the robot would not be quite sure what the task is, and it might be actually producing a solution that is wrong one. So what we can do essentially is just ask for continuous sections. However, such a continuous section, namely such a motion planner, usually is not possible. This is just a phenomenon that one will find. Namely, if you know how to plan the motion between any 2 points, then you just keep one fixed, and the other one you can plan the motion to this fixed. All other points can be moved to the fixed point through this motion planner, and that would just give a contracting homotopy of the space. So in practice, this is not possible, and we have to deal with this problem in concrete instances. So what Farber proposed is to look at the Schwartz genus of this evaluation map. Just look at the minimal number of open sets where you actually have such a continuous section. So this defines for us a number, a positive integer, TCX, that depends on, it's actually depends only on the homotopy type of X, that somehow captures this problem provoked by noise. Here's, for people that is not quite familiar with this concept of sectional category, let me just say very briefly what this amounts to. Essentially, here's a picture of the space of states of a given space of states of a given robot, and that has been divided into 6 chunks, 6 pieces. Let me call each one of these a domain. Now, one would be asking to have a solution, a continuous solution, at least for all the tasks lying in each one of the domains. In this case, I have 6 domains and 6 different possible routes of solving tasks. Okay, now what's the problem with this situation? Of course, here is a task, and this picture represents that this task is close to 2 different domains. So in the presence of noise, the robot may not be quite sure what domain it belongs to and what solution it should apply. So it has a 50-50 chance of actually applying a wrong solution. And of course, the situation is even worse for this task. So what this number, TCX, does for us is to give a way of recognizing motion planners, this information, these domains and the partial and the local liftings. To such information, I will call a system of motion planners, the domains and the local sections. So this number gives us a way to recognize systems of local motion planners which best minimize the effect of noise in the following sense. It is essentially what Farber proved is that if you're given such a system of local motion planners, then no matter what, you will always have, at least a point, a task which is close to TCX domains. So this is very bad news because you cannot do better than this number. The good news is that there will always be a system of motion planners so that it actually, every task is close to at most this number, TCX of domains. And actually there is an optimal, an ideal motion planner which has actually TCX domains. Space of tasks, right? So, okay, so this gives us, this is the idea of this invariant, of course. Then one wants to study it with techniques of homotopy theory and topology in general, and well, this is what I'm trying to describe. Now, let me, for the purposes of this talk, want to mention two variants, two generalizations of this invariant, TCX, Farber's TCX of TC of a space X. Namely, there is a Farber-Grant symmetric topological complexity, which essentially measures the same thing, but when one restricts the motion planners to be symmetric. Namely, if you know how to move from a point A to B, then the solution for the backwards task should be just moving backwards through the same path. So this adds some kind of efficiency condition to the motion planner, to the system of motion planner. There is also Rudiak's generalization of Farber's TC, which is also called a sequential motion topological complexity or higher topological complexity. And this is, again, the same thing. Perhaps it's a more natural application because here the tasks are represented not only by a pair of points, initial final points, but also a sequence of intermediate points. And a solution for such a task is not only a path that should start and end in the prescribed points, but it should also visit in sequence the additional given points. So these all are, except for the Farber's grant, that's not a homotopy invariant, but most of these things are homotopy invariant. That's not difficult to see. So at this point, I'm ready to describe for you the first connection between Sam's contributions, fundamental contributions to the immersion problem of manifolds and in particular of real projective spaces. Namely, let me start by saying that just as a Lusternik-Schneiderman category of a space, TC of X is a homotopy invariant, although it's a little bit more subtle. It captures a little bit more of what is going on in there. For instance, in the case of real projective space, the category is easy to compute. That's just the dimension of the space. However, the topological complexity of that manifold actually agrees with the smallest dimension of Euclidean spaces where this manifold can be immersed. So this is very surprising. I will be adding some comments about this. There is also a version about symmetrized topological complexity. Namely, if you forget about immersions and ask about embeddings of Euclidean embeddings of real projective space, then it turns out that this embedding dimension agrees with Farber-Grant symmetric topological complexity. In other words, describing embeddings of real projective space into Euclidean space is nothing but producing efficient systems of local motion planners for RPM. Now, although the embedding result is a little bit more technical to prove, turns out that the immersion result, Farber's result with Abakikov and Sergei Juzvinsky, is really very simple to prove in retrospective. Namely, once one knows the work of Sam, namely, Sam proved that having an immersion of RPM into K dimensions, Euclidean dimensions, is the same as having, I'm going to erase this. Oh, sorry. It's the same as having an actual map, PK. In the sense, it is actual in the sense that if you restrict it to the axis, then it is it is essential. In particular, it has to be trivial, null homotopic on the diagonal. Here I'm supposing that K is larger than M. Now, if you take that for granted, then the proof of Farber's result is very simple because we all know that this can be covered by the spaces, the universal covers. And to such a map, you have, it is covered by a bilinear, by equivariant, a CMOD2 bi-equivariant map. In other words, a map that takes out signs here if you keep one of the other coordinates fixed. So now the point is that one of these bi-equivariant maps has all the information to producing a system of local motion planners for the projective space. Namely, how can you plan the motion between two lines, 2 points in the real projective space? So you have 2 lines through the origin in some large Euclidean space, dimensions k plus 1, n plus 1. So it's a very simple-minded way of planning the motion, namely you just rotate one of the lines to the other through the plane that they generate. The problem, of course, is that you have to say in which direction, say sweeping the shorter angle. The problem, of course, is when the lines are perpendicular and you don't know where side you should rotate. So this is essentially the lack of continuity of the motion planners. But once you have this information, then you can do the following planning. You can take your two lines and choose a pair of unital vectors on the lines. And if this condition holds, namely this is the jth coordinate of this function. There are k plus 1 coordinates. If this is positive, then I could just say that I'm going to move L0 to L towards L1 by moving x0 through x1 through the shortest angle. This is okay. This takes into account the situation where the lines are perpendicular. Notice that this does not depend on the selected vectors, because if you change this for the opposite, then this will change in sign, because you have a C2 by covariant map, and this would not be the case, so you actually have to change also the other one. And now moving from the 0 to the 1 is compatible with this motion. So this is well defined, this is continuous. And now the problem is what happens if the two lines are the same? If the two lines are the same and the vectors that I choose with this condition are opposite to each other, then you don't really know which direction to move. In what dimension? And there are two possibilities. There are actually an infinite number of possibilities. So, but this situation is overruled because the fact that this is an actual map, namely, as I said, this is null homotopic on the diagonal, which means that you can take it to be constant in the diagonal. So this is constant on the diagonal, say with value 1, 0, 0. So that condition will only hold on the diagonal. So dj x0, minus x0 will be either 0 or minus 1. So there you are not facing that problem, and you have a continuous system, a system of local motion planners. Okay, so that's this situation. Now let me say a little bit about, well, at this point you could ask, what's so special about that equality? DC being equal to the immersion dimension of a given manifold. This is true for then real projective spaces, but in a sense this is true basically that I know of, and it seems like only for the family of real projective spaces, and it immediately fails in some concrete situations, namely if you take spheres, then it turns out that it is not difficult to see that the topological complexity of a sphere is either 1 or 2, depending on the parity of the dimension. Is 1 when m is odd, and is 2 when m is even. And of course, this is independent of the dimension of the sphere, which is embedded and immersed in one higher dimension. Now, more generally, the topological complexity of configuration spaces of k points, k order points in Rd, if you take k equals 2, you essentially have here, it's independent of the dimension of the Euclidean space. It's independent of D. It basically depends on, it's roughly twice the number of points. And on the other hand, even the dimension of this space is, depends on k. It's actually, and D, more importantly, it is dk. It is also worth mentioning what happens for complex projective spaces, namely the immersion problem for complex projective spaces is also an open problem. It might be a little bit more simpler to consider, but still is open, and yet the topological complexity of complex projective spaces is easy to compute. More generally, this is true for any closed, simply connected manifold with a symplectic structure. So this is telling us that This equality is kind of an accident or a really very special case in the case of real project spaces. Now, to tell you the truth, these examples do not do justice to the singularity of this equality for real project spaces, because it is not difficult to see that the topological complexity of a space decreases as the connectivity of the space increases. So in all the cases that I discussed, we have simply connected spaces. So one should actually be looking to other families of spaces that are closer to real projective spaces. And well, the obvious generalizations do not work. Namely, here's some work, still some of it is still in progress, but length spaces, the quality fails. Actually, length spaces, as the torsion increases, behave like complex projective spaces, and you can actually compute DC of those things. And of course, length spaces have a cyclic, non-trivial fundamental. Complete flat manifolds, which are very natural generalizations of real projective spaces, also fail, and they have a two elementary abelian group. So. But the situation is even more interesting in Davis's generalization of real projective spaces, the so-called projective product spaces, which also have fundamental group in CMO2, and the situation here is also very dramatic and fails. This equality is false for those spaces. So I'm not going to be saying more things about that. The point is that, well, this is a connection between something that Sam did at the really beginning of his work and connecting with some problems in actual applications, at least a language for doing it. So at this point, let me make a pause. Before going into the second application, let me kind of propose a problem, a challenge. Namely, in the immersion problem, Euclidean immersion problem for manifolds, and in particular for real projective spaces, together with his collaborators, Mark Mahowald, Ed Brown, Jose Adam, Sam laid the foundations for a very effective, computable way of handling homotopy obstructions that arise in this immersion problem, some way or other. So the question is, what about, see, this is also a sectioning problem too, can be interpreted as a sectioning problem. And, but of course you can do standard obstruction theory, but that's not much hope for doing some, well, actually there are some results on that direction, but eventually one will stop. We'll have, very soon, one will have to stop with these computations. So the question is, well, can you extend, say, this approach via modified Postnikov towers so that you can actually do, for instance, you can actually do an effective handling of homotopy. So, and this allows me to go to the next application, namely, yesterday, Fred Cohen already, at the end of his talk, he mentioned some nice connection between toric topology and robotics. Namely, the robotics guy, as Fred explained me, can use the language of certain polyhedral product space to codify somehow the way that a spider walks. So here is a little contribution on this direction, still a little bit in progress, and of course it has to do with the recent work on Sam on toric topology, and this is a small contribution to this toric festival. So what we, let me start by saying that TCN, higher versions of topological complexity, give a sort of a shuffled interpretation of the category of powers of a space. Namely, the nth topological complexity of a space sits somewhere in between the category of the nth power and the category of the n minus first power. Now, these inequalities are sharp in the sense that there are always examples where either one of these two inequalities are actual equalities. For instance, if you take an H space, it doesn't have to be a homotopy associative. The first inequality is actual inequality. That's a result of Gregory Lupton and Jerome Schroeder. Also, on the other side, the upper bound becomes an equality for manifolds with a symplectic structure with no fundamental group and which are closed. So the question then is, what happens with the intermediate possibilities? Namely, except for the spaces that I want to motivate here at this moment, for all other spaces where topological complexity can be computed, it turns out that this number agrees with either one of the two bounds. Or at least it differs at most by one by the bounds. And usually, obstruction theory, the first obstruction theory, the cohomological one, in the classical sense, does the solution of this one gap. But then one would be asking, how can you produce an example of a concrete space where TC of X is, say, right in the middle of the two bounds? And, well, this is an interesting problem because obstruction theory, homotopy theory, would not be so well suited for doing that because you would have to go through a lot of obstructions. You know how this works. So the point is that toric topology essentially deals with spaces with a lot of course, with a lot of rich topological structure. And in those cases, you can actually do alternative things to actually compute the topological complexity, higher versions of topological complexity of X. Okay, so let me describe a little bit of that. So I want to describe, let me focus on the case when n is 2 of this inequality. That one. So can I describe a space so that if this number is given, so suppose you give a number k and a number L, which is somewhere in between k and 2k. And then I want to describe a space, and this is already been given in advance. I want to describe a space so that its topological complexity lies in between the category of X and the category of X times X. Well, this has been actually done in a very concrete example, which I want to discuss, by Dan Cohen and Goretsis Pruzzi, which is a former student, a PhD student of dance. And let me describe this situation for you. So what you can do, so look at the polyhedral product determined by the pair S1, a point. This is up to homotopy, the one that these applied guys are using for codifying the movement of this robot with many legs. And this is then the polyhedral product determined by this pair, and depending, of course, of a given simplicial, abstract simplicial complex, K. So this has a very natural structure. Actually, it is a subspace, it's a subcomplex of the m-dimensional torus. K here is a simplicial complex on n vertices. And so you look at Tm, and you take the minimal cell decomposition on that thing. In other words, you have the circle. This has two cells. And then you take the m power of the cell decomposition. So that describes for you cells indexed by subsets J of 1 to m, and where the J cell, J, is determined by all such tuples, so that the I coordinate is, as we know, the fixed point, the base point, precisely when this coordinate does not belong to the simplex J. And in these terms, then xk is just the union of those cells determined by the complex K. Okay. So now There is a general lower bound for topological complexity. This is something very simple, basic. Namely, the topological complexity of a space, this is a general result. This is a particular case of a more general result. TC of X is bounded from below by the zero cup length of the space. What is that? Sorry? So what you have to do is consider the cohomology algebra of X and look at the zero divisors. The zero divisor is just a pair, A comma B, so that the product is zero. None of those are zero. None of the factors is zero. Or more generally, a zero divisor is an element, think of A tensor B, is an element here which lies in the kernel of the cup product. So the zero divisor's cup length is the largest possible number, it's the largest possible product of elements in the kernel of these zero divisors, so that the product is non-zero. And that largest possible number is very easy to see, that's denoted by this zero cup length of X, and that gives a lower bound for the topological complexity of X. Well, at this point, Cohen and Pruzzi prove that this is actually an equality in the case for xk in that situation in transparent. And what they do is actually produce, once they have this lower bound, what they do is, well, they use the rich structure in the topology just to define for you on the nose an explicit system of local motion planners with that amount of domains. So that does it for you. You have the minimal also. Now, at this point, I should mention that there is a gap in that argument. Namely, about a month ago, a little bit more than a month ago, I organized a student workshop in Abacus, a recent research center for applied mathematics. And Farber and Dan Cohen were in some of the invited speakers. They gave very nice talks. Dan talked about this example. I said, let's work on that and let's generalize it for TCN. And at the end of the couple of days that they were there, this group of students kept working on which I don't see here. Maybe they know already the answer. They kept working on the problem, and we found this gap. So I believe the gap is reasonably easy to fix. Actually, a subgroup of these students is still working on fixing this and working on several generalizations. But the point of all this is that the ideas about using the rich structure in toric topology should be generalizable, not only for this example. One should be able to compute TC of many more families of spaces and actually push the theory in several directions. For instance, one direction, there are three things that I want to mention here. Before mentioning this, I mentioned, what about obstruction theory? This is difficult if you can modify it somehow so it is handleable, at least a little bit more handleable. Then you can actually push the calculations, but also the theory. For instance, for the category, the Lustermann-Zimmermann category of a space, there is a conjecture, the Ganeas conjecture, that says that this category is subadditive. Well, this is easy to see. This is subadditive. Category of a sphere is 1. And the conjecture is that it is always an equality. The conjecture was that this was always an equality for all spaces. We now know, by work of Norio Iwase, that there are actually some spaces which essentially have torsion. I believe there are 2 cell complexes for which the category does not increase. It stays the same. It cannot go lower than that. So it would be very interesting to have something theoretical that allows us to prove a version of a TC version for the Ganea conjecture. or disprove. Most likely it will not be true. For instance, the Ganea conjecture. So, for instance, topological complexity, just as its relative category, is additive. In particular, this satisfies that this is less than or equal to Tc of x plus Tc of the sphere, which is either 1 or 2. And actually, the three possibilities should hold. Namely, there are cases when x itself is a product of spheres in which it increases by 2, namely when the sphere is of dimension even. Or if it is of dimension 1, it actually increases by 1. But there should be spaces x where the topological complexity should stay the same, and it would be very interesting to describe them. So this is one of the interests in having some kind of a theoretical tool. The other, let's see, the other is, well, on the computational side, you would like to be able to compute TC of as many spaces that you find in nature, and for practical purposes especially. And, but also, and as I said, toric topology should be a very fertile ground to try these ideas. But you would also like to prove general results. And another such result was proposed by Farber himself, saying, well, what about topological complexity of Euler-MacLane spaces of type pi 1? So suppose you take a finite group. And the idea is, well, how can you describe this number in terms of a purely algebraic setting, something that depends just on the group? Like in the case of the category, so that the category of one of these things is basically the cohomological dimension of the group. So what about these things? And well, using these ideas on toric topology, one can actually do these kind of things for a large family of groups. For instance, you can take an arcing group, a right-angled arcing group, namely a group arising from a graph, a simplicial. So suppose you have a simplicial graph. Now, given such a thing, you can construct something that apparently is called the flag complex associated to this graph, which is nothing but just throwing in all possible higher simplices that the graph supports as being the one-dimensional skeleton. In other words, for every click of the graph, you add one simplex. And now you have a simplicial complex, and then you could consider this guy, and it turns out that this has the homotopy type of a subcomplex of that guy, of TM. Is one of these guys. Sorry, I don't know what did I say. This guy, of course, has the homotopy type of itself. But this guy has the homotopy type of an Eilenberg-MacLane space of type the group that I was given, the right-angle group, comma 1. And in particular, you can describe this number in terms of, you can describe this, when this is a right-angle arcing group, in terms of this, because it's inequality for this kind of guy. And this number, of course, is given up there. It is just the maximal of the sum of the length of simplices in K so that they are disjoint. But it's not the couplet. But this is not usual zero divisors cup length. Zero divisors cup length. As a joint? No. They have to be disjoint. Maybe the situation will get clearer in what I will say next. But the point of everything that I said is that, up to here, is that the topological complexity of these Euler-MacLane spaces for right-angled arcing groups, is described very explicitly in terms of combinatorial information of the graph. So there's another, oh yeah, But the thing is, this is related. This describes the PC of this island of McLean space, as I define it.
Maybe we could do the questions at the end. Proceed.
Okay. The other thing is already Fred mentioned it, namely, you can look at the complement of arrangements of hyperplanes, complex complements of a complex hyperplane arrangement. And as Fred mentioned, for instance, you can have these things arising in terms of the other, let me just ground my bit. The example that you mentioned about the polyhedral product D2, D2, S1. That's, yeah, so that's what I'm saying. That's my case. So I started with a graph, the one skeleton of that black mass, of that black complex. Exactly, exactly. So the other is a complement of arrangements of hyperplane, complex hyperplanes. And as Fred said, they also rise in terms of, they have the homotopy type of polyhedral products. And in particular, more generally, they don't have to be arrangements of coordinate hyperplanes. You can take any arrangement, any arrangement of hyperplanes, complex hyperplanes, as long as they are in general position. And the same thing happens. They have the homotopy by an old theorem of Hattori. They have the homotopy type of one of these guys. So you know, actually, the topological complexity of those things. So let me finish. How much time do I have? Great. So let me finish by giving you an explicit example of this situation that I proposed at the beginning, namely, given two numbers, k and l, with l in between two, k and k, produce an explicit, very simple-minded space so that its topological complexity is L and the category is K. Well, this is very easy. There's nothing to compute. This is due to Rudiak, Julie Rudiak, although with other methods. Think of the wedge sum of two tori sitting inside TM. So I have, k coordinates, and the first k coordinates and the last m minus k coordinates. This sits very naturally inside Tm. Well, the category of this space is very simple. The category of a wedge is just the maximal, as long as they are well pointed, is just the maximal of the categories of the sums. So in this situation, the category of each of the summands is just the rank of the dimension of the torus. And so this is k, essentially. This is the largest between k and n minus k, and because of this condition, this is just k. But on the other side, well, this wedge sum is nothing but this polyhedral product for this abstract simplicial complex given as all simplices in the first k coordinates and the last simplices in the last one. So here what one gets is that, well, then one knows what is the topological complexity, namely is this number. And, well, you have to find the simplices, which are disjoint, simplices of k, and a very natural one is the maximal one here and the maximal one there. So these are the lengths, and the sum is m, and so one has this number, prescribed number. So the idea is that one should be able to use toric topology to actually push these kind of ideas. Thank you very much, and feliz cumpleaños.
running a bit behind. We have time for a quick question.
The results in the literature for Sn comma point K a graph and these quadratic algebras are nice, so you might be able to get a complexity result in that more general case.
Sure, sure.
But you got just
Yeah, but you would have a lower bound. The point here is that you would have only the lower bound given by the zero divisors complement. And you would have to move your hands to produce actually, or some way or other, produce your system of local motion planners. And with some hope, you would get a quantity.
So what you are saying is that in the case S1 comma point, that your zero cup length is the same as a topological complexity,
right.
But for more complicated space, it may be not the case.
I don't know.
Right.
It might be.
Okay.
But it's worth it.
Okay, well, let's thank the speaker one more time. And without any break, we move on to the next lecture. I believe Martin Bendersky. Where is he? We're gonna, I guess there's no break. The program says no break. The program says no break.